Ladies and gentlemen, what if I told you the moon contract wasn't won in a boardroom? It was won on the factory floor? Not with promises, not with PowerPoint slides, but with steel, fire, and rockets that actually fly. While others designed concepts, one company built real hardware, tested it to failure, and came back stronger every single time. This isn't just about landing on the moon. It's about building a transportation system that makes space affordable, repeatable, and unstoppable. And once you understand the real reason behind this decision, you'll never look at the future of space exploration the same way again. And the real reason SpaceX won the moon lander contract is not about luck, politics, or hype. It's about engineering culture, vertical integration, and a relentless obsession with first principles thinking. The same mindset that transformed the electric vehicle industry and redefined what's possible in advanced manufacturing. When NASA evaluated proposals for the Artemis human landing system, they weren't just choosing a spacecraft. They were choosing a philosophy of execution. And at the center of the decision was Artemis program, a mission to return humans to the moon and build a sustainable presence there. Sustainability changes everything. This isn't about a single symbolic landing. It's about repeatability, cost efficiency, cargo capacity, and scalability. And scalability is where the difference becomes undeniable. And the proposed lunar lander is derived from Starship, a fully reusable launch and deep space transportation system, engineered from the ground up for mass production. Stainless steel construction, methane-fueled Raptor engines, orbital refueling capability. Every design choice optimized for rapid iteration and high flight cadence. Instead of designing a one-off fragile lunar module, the architecture leverages a vehicle already in aggressive development for Mars and deep space missions. And cost matters. Not in the traditional aerospace sense of shaving small percentages off billion-dollar overruns, but in fundamentally rewriting the cost curve. Full reusability means hardware isn't discarded after one mission. High payload capacity means fewer launches are required to move meaningful mass to lunar orbit. Vertical integration means engine structures, avionics, and software are built in-house, reducing supplier dependency and compressing timelines. The same production logic that scaled electric vehicle manufacturing applies here. Build, test, refine, repeat at speed. And risk reduction was another decisive factor. Unlike legacy contractors that rely on extended design phases and theoretical validation, this company builds hardware early and tests it publicly. Rapid prototyping isn't a buzzword. It's a workflow. Explode, analyze, improve, relaunch. Each iteration compounds knowledge. By the time lunar operations begin, the core vehicle will already have accumulated extensive flight data from orbital and deep space missions. That operational maturity is critical when human lives are involved. And then there's payload capability. Traditional lunar landers were designed for minimal crew and limited cargo, optimized for weight constraints tied to expendable rockets. Starship-class architecture changes that constraint entirely. Large crew cabins, significant surface cargo, infrastructure components for long-term habitation. Instead of planting flags, this approach enables building foundations. And orbital refueling also shifts the paradigm. By launching tanker variants to refuel a lunar-bound vehicle in Earth orbit, mission planners are no longer restricted by a single launch vehicle's mass limits. This modular fueling architecture enables heavier payloads to travel farther at dramatically lower costs per kilogram. It's systems-level thinking, solving the transportation network rather than a single trip. And there's also alignment of long-term vision. The moon is not the final destination. It's a proving ground. Technologies required for sustained lunar operations, life support, reliability, in situ resource utilization, deep space navigation, are directly applicable to Mars. Selecting a lander derived from a Mars-optimized vehicle creates continuity. Investments made for Artemis directly accelerate interplanetary capability. That strategic overlap reduces redundancy and maximizes return on development spending. And financial structure played a role as well. The proposal required significantly less funding than competitors, in part because much of the development cost is already internalized within the broader Starship program. When a company is already investing billions of private capital into a reusable launch system, NASA benefits from that parallel momentum. Government funding amplifies existing progress instead of initiating it from scratch. And manufacturing infrastructure cannot be overlooked. High bay assembly facilities, automated welding systems, engine production lines operating at unprecedented cadence. The same industrial discipline that scaled battery gigafactories translates into spacecraft production throughput. Speed is not chaos, it's controlled acceleration driven by data. And ultimately, the contract reflects a shift in aerospace philosophy. Move fast test often designed for reuse and scale like a technology company rather than a traditional defense contractor. The moon demands more than heritage. It demands reinvention. And reinvention favors organizations willing to challenge legacy assumptions, vertically integrate critical systems, and accept short-term volatility for long-term transformation. And the real reason is simple. When the objective is sustainable lunar presence and long-term interplanetary expansion, the winning solution isn't the safest-looking proposal on paper. It's the one engineered to scale beyond the mission itself. And the ripple effects extend beyond a single contract. A reusable lunar architecture forces the entire aerospace ecosystem to rethink assumptions about cost, cadence, and capability. When hardware is treated as a long-term asset, rather than a disposable artifact, engineering priorities shift toward durability, maintainability, and rapid refurbishment. This is the same shift that accelerated electric mobility. Design systems that improve with iteration, not ones that reset after every cycle. And software plays a central role in that transformation. Modern spacecraft are no longer defined solely by propulsion and structure. They are defined by code. Guidance, navigation, and control systems evolve continuously through updates. Simulation environments model thousands of flight scenarios before hardware ever leaves the pad. Telemetry streams are analyzed in real time, feeding machine learning models that identify anomalies before they become failures. A vehicle designed with software-first architecture gains compounding advantages over time because every mission enhances the intelligence of the next. And supply chain strategy reinforces that advantage. Vertical integration reduces friction between design and production. When propulsion engineers collaborate directly with manufacturing teams under one organizational structure, iteration cycles compress dramatically. Changes that might take months in a fragmented contractor ecosystem can be implemented in weeks. This speed is not reckless. It is data-driven acceleration supported by tight feedback loops and direct accountability. And infrastructure on the ground mirrors ambition in orbit. Launch sites built for rapid turnaround reduce bottlenecks. Propellant production systems engineered for scale support high flight frequency. Test facilities operate continuously, validating engines and subsystems at a pace previously unseen in orbital-class programs. Every element of the system is optimized for throughput because cadence is the multiplier of progress. A vehicle that flies once a year evolves slowly. A vehicle that flies monthly then weekly compounds knowledge at exponential rates. And the lunar mission profile itself reflects systems thinking. A heavy lift launch places the lander into Earth orbit. Tanker missions rendezvous and transfer cryogenic propellant through precision docking operations. Once fully fueled, the vehicle performs a translunar injection burn, enters lunar orbit, and descends to the surface with substantial margin. Each step leverages technologies already proven or actively tested in parallel programs. Redundancy is embedded into propulsion power, and life support subsystems ensuring resilience under harsh lunar conditions. And surface operations benefit from scale. Larger habitable volume allows astronauts to work more effectively and safely. Expanded cargo capacity enables delivery of rovers' power systems and scientific instruments in a single campaign. Instead of multiple small missions delivering fragmented infrastructure, a single architecture can transport integrated systems. That efficiency reduces mission complexity and lowers cumulative risk. An energy strategy further distinguishes the approach. Solar arrays designed for modular deployment can power surface habitats. Battery systems engineered with lessons from high-density automotive packs provide reliable storage through lunar night cycles. Thermal management solutions refined through years of electric powertrain optimization translate directly into spacecraft environmental control systems. Cross-industry innovation accelerates capability because breakthroughs in one domain cascade into another. And financial sustainability is equally critical. When cost per kilogram to orbit declines dramatically, mission planning shifts from scarcity to abundance. Scientists can propose experiments that were previously mass prohibitive. Engineers can design habitats with structural margin instead of trimming every gram. Abundance changes creativity. It unlocks bolder architectures and longer-term thinking. And international collaboration also becomes more feasible under a lower-cost regime. Partner agencies and commercial payload providers gain access to lunar transport without bearing the full burden of bespoke vehicle development. A standardized high-capacity lander functions as infrastructure, a platform upon which others can build. Infrastructure multiplies opportunity. And there is also a cultural dimension that cannot be ignored. Teams operating under aggressive timelines develop a bias toward action. Problems are confronted directly through testing rather than deferred through documentation. Hardware is viewed as a prototype until proven otherwise. Failure when it occurs is dissected publicly and converted into immediate design improvement. This transparency fosters trust among stakeholders who value measurable progress over polished presentations. And regulatory navigation reflects similar pragmatism. Certification pathways are integrated early into development cycles. Safety reviews are conducted in parallel with hardware iteration, rather than sequentially at the end of design phases. This concurrent approach shortens overall timelines while maintaining rigorous standards for crewed flight. And the lunar environment itself demands innovation. Extreme temperature swings, abrasive regolith, and communication delays challenge traditional design assumptions. Stainless steel structures offer resilience against micrometeoroid impacts and thermal stress. High-thrust methane engines provide controllable descent profiles. Autonomous landing algorithms enable precision touchdown, even with limited real-time input from Earth. Each design choice reflects adaptability rather than adherence to legacy norms. And beyond the Moon, the same architecture positions humanity for deeper exploration. Orbital refueling, large payload capacity, and reusability are not incremental upgrades. They are foundational shifts. When transportation becomes reliable and routine exploration transitions from rare expeditions to sustained operations, the Moon becomes a training ground for building closed-loop life support, resource extraction systems, and autonomous construction technologies. And in that context, the contract represents more than a procurement decision. It signals confidence in a new model of aerospace development, one that merges Silicon Valley iteration speed with industrial-scale manufacturing discipline. It rewards measurable hardware progress over conceptual heritage. It aligns public exploration goals with privately driven infrastructure expansion. And the underlying principle remains consistent. Engineer the system to scale, integrate vertically to move faster, test relentlessly to learn faster still, and treat every mission as a stepping stone toward a multiplanetary future where transportation is no longer the limiting factor. And transportation is the foundation of civilization, whether across continents or across celestial bodies. When launch costs drop and reliability increases, entirely new economic layers emerge. The same pattern that followed the advent of commercial aviation and global internet infrastructure now begins to unfold in orbit. Lower barriers enable more participants. More participants drive more innovation. More innovation accelerates capability. This flywheel effect is not theoretical, it is engineered. And at scale, lunar logistics transform from isolated missions into supply chains. Cargo manifests become diversified. Scientific payloads share space with construction materials. Autonomous robots precede crews to prepare landing zones and deploy power grids. Every kilogram delivered builds momentum for the next campaign. Instead of restarting from zero with each mission, assets accumulate on the surface, forming the backbone of permanent presence. And cryogenic fluid transfer, once considered experimental, becomes routine. Precision docking systems operate with centimeter-level accuracy. Thermal insulation technologies preserve propellant stability across extended orbital loiter periods. These engineering challenges are solved not through incremental paperwork, but through full-scale demonstrations. Real hardware, real data, real iteration cycles. Confidence grows from flight history rather than simulation alone. And human factors engineering evolves in parallel. Spacious interior volume enables ergonomic workstations, radiation-shielded rest areas, and adaptable mission layouts. Environmental control systems leverage high-efficiency heat exchangers and closed-loop filtration architectures. Crew interfaces prioritize intuitive design, minimizing cognitive load during critical operations. Lessons from automotive user experience. Simplified controls, large touch interfaces, streamlined feedback systems migrate naturally into spacecraft cabins. And on the surface, modularity defines expansion. Habitat elements are delivered in scalable units. Power systems interconnect seamlessly. Communication arrays link lunar installations with Earth and orbital relay satellites. The objective is not a symbolic footprint, but operational continuity. Reliability metrics guide every decision. Mean time between failures, component redundancy ratios, maintenance cycle thresholds. And data infrastructure extends beyond telemetry. High-bandwidth communication channels allow continuous streaming of operational metrics back to mission control centers. Advanced analytics platforms process this information in real time, identifying patterns that optimize fuel efficiency, thermal regulation, and life support performance. Predictive maintenance reduces downtime. Artificial intelligence assists in navigation adjustments and landing site hazard detection. And manufacturing techniques pioneered for terrestrial gigafactories influence extraterrestrial strategy. Automated welding, modular assembly lines, and digital twin simulations compress development cycles. The same philosophy that scales battery production applies to engine manufacturing. Standardization reduces variability. Volume reduces cost. Continuous improvement elevates quality. And regolith utilization technologies begin transforming lunar soil into construction materials. In situ resource utilization reduces dependency on Earth-supplied components. Oxygen extraction experiments support life support and propellant production. The long-term vision prioritizes autonomy. Every kilogram produced locally increases resilience and lowers logistical complexity. And safety remains paramount. Multiple engine-out capability ensures descent stability, even under partial failure. Distributed avionics architecture prevents single-point system collapse. Power redundancy protects against extended lunar night conditions. Emergency ascent trajectories are pre-programmed and tested repeatedly. Crew survivability drives structural reinforcement and shielding strategies. And economic models adapt alongside technical frameworks. Commercial payload providers gain access to standardized lunar transport slots. Research institutions plan multi-year surface experiments. Private partnerships fund infrastructure in exchange for utilization rights. The Moon evolves into a platform for experimentation in materials science, biology, and energy systems under reduced gravity conditions. And public engagement also shifts. High-definition mission broadcasts, transparent testing updates, and visible iteration cycles cultivate global interest. When development is observable rather than concealed, momentum builds organically. Students pursue aerospace engineering inspired by tangible progress. Suppliers innovate to meet new performance benchmarks. And energy generation strategies explore nuclear and advanced solar hybrids to ensure uninterrupted power during prolonged darkness. Thermal radiators manage extreme temperature gradients. Dust mitigation technologies protect seals and joints from abrasive interference. Each subsystem reinforces overall mission durability, and the long-term architecture integrates seamlessly with deep space objectives. Orbital refueling depots become waypoints for Mars-bound missions. Life support systems validated in lunar orbit scale for interplanetary transit. Structural designs tested against micrometeoroid exposure inform future spacecraft hull improvements. Knowledge compounds across programs, and mission planning transitions from conservative single-launch paradigms to dynamic multi-launch orchestration. Tankers, cargo ships, and crewed landers operate in coordinated sequences. Software algorithms optimize launch windows and propellant allocation. Autonomous rendezvous reduces operational overhead. And cultural alignment across engineering teams sustains momentum. Rapid decision-making processes replace prolonged committee cycles. Hardware readiness reviews focus on measurable criteria. Cross-disciplinary collaboration eliminates silos between propulsion software and structural departments. And the broader impact extends into Earth-based industries. Advances in high-strength alloys influence automotive safety designs. Cryogenic storage breakthroughs enhance energy grid resilience. Autonomous navigation systems improve terrestrial transportation networks. Space innovation cascades into everyday life. And as cadence increases, reliability metrics climb. Each successful landing strengthens statistical confidence. Insurance models adjust to reflect improved risk profiles. Investment flows accelerate further development. The ecosystem becomes self-reinforcing. And through disciplined engineering, vertical integration, and relentless iteration. Lunar exploration transitions from episodic spectacle to scalable infrastructure, redefining what sustainable presence beyond Earth truly means. And sustainable presence beyond Earth truly means designing for permanence rather than publicity. It requires shifting from mission-based thinking to ecosystem-based thinking. Vehicles are not isolated achievements. They are nodes in a transportation network. Landers connect to orbital depots. Depots connect to launch sites. Launch sites connect to manufacturing hubs. Each layer feeds the next in a closed-loop architecture engineered for resilience and scale. And resilience begins with materials. Stainless steel, chosen for strength, cost efficiency, and thermal tolerance, performs reliably across extreme temperature gradients. Unlike exotic composites that demand complex fabrication environments, steel enables rapid welding, straightforward inspection, and field repair potential. Durability is not an aesthetic choice. It is an operational advantage when infrastructure must endure repeated launches, deep space radiation, and abrasive lunar dust. And propulsion strategy reinforces that durability. Methane-based engines offer cleaner combustion compared to traditional kerosene systems, reducing soot buildup and extending engine life. Reusability depends on minimizing refurbishment time between flights. Engine health monitoring systems collect vibration signatures, pressure differentials, and thermal readings throughout each burn, feeding predictive maintenance models that determine component replacement cycles before degradation impacts performance. And thermal protection systems undergo continuous refinement through flight testing. Instead of assuming perfection in early design stages, tiles and shielding elements are iterated based on real atmospheric reentry data. Data density increases with each mission. Margins tighten intelligently. Weight decreases without compromising safety. Engineering confidence grows from repetition. And launch cadence acts as the ultimate force multiplier. The more frequently hardware flies, the faster improvements propagate. This mirrors the scaling logic of high-volume electric vehicle production, where iterative refinements compound across thousands of units. In aerospace, frequency was historically constrained by cost and expendability. Reusability dissolves that constraint, unlocking learning velocity previously unattainable. And autonomy becomes increasingly central. Lunar landing sequences rely on advanced terrain relative navigation systems capable of identifying hazards in real time. High-resolution cameras feed onboard processors that compare live imagery against preloaded surface maps. Micro-adjustments in thrust vectoring ensure precision touchdown. Autonomy reduces communication latency dependence and enhances crew safety. And on the surface, robotics extend human capability. Autonomous construction units deploy landing pads to mitigate regolith plume effects. Power arrays unfold and self-orient toward optimal solar exposure. Mobile platforms transport cargo modules to designated assembly zones. Humans supervise and refine rather than perform every task, manually maximizing efficiency in low-gravity environments. And life support architecture embraces closed-loop principles. Water recovery systems recycle humidity and waste streams with high efficiency. Carbon dioxide scrubbers regenerate continuously rather than relying on disposable cartridges. Food production experiments explore controlled environment agriculture, optimized for lunar gravity conditions. Each closed loop reduces dependency on Earth resupply. And radiation mitigation strategies integrate layered shielding water walls and regolith-based barriers. Habitat modules are positioned strategically to leverage natural terrain protection. Continuous dosimetry monitoring ensures exposure remains within safe limits. Safety engineering is proactive rather than reactive. And communication infrastructure scales alongside habitation. Lunar surface antennas connect to relay satellites in orbit, ensuring uninterrupted contact with Earth-based mission control. High-bandwidth links enable telemedicine consultations, remote software updates, and scientific data transmission without delay. Connectivity supports both operational efficiency and psychological well-being for crew members. And economic scalability remains central to long-term sustainability. As launch costs decrease further, private industry participation increases. Manufacturing experiments in reduced gravity open pathways to materials impossible to fabricate on Earth. Pharmaceutical research explores protein crystallization in lunar environments. Commercial incentives align with exploration objectives, reinforcing infrastructure investment. And training protocols evolve to reflect increased mission frequency. Astronaut preparation incorporates virtual reality simulations integrated with real mission telemetry. Engineers rehearse contingency scenarios using digital twins synchronized with operational spacecraft. Continuous learning loops ensure readiness improves with each campaign, and energy independence advances through diversified generation systems. Large-scale solar farms expand incrementally. Compact nuclear reactors provide baseline power stability. Energy storage units derived from high-density battery technology buffer fluctuations. Grid architecture is modular, allowing incremental expansion as settlement grows. And surface mobility solutions leverage electric drivetrain advancements. Pressurized rovers utilize efficient battery packs optimized for low-temperature operation. Regenerative braking recaptures energy during descents across uneven terrain. Maintenance procedures remain streamlined due to standardized components. And environmental monitoring stations collect data on seismic activity, temperature variance, and regolith movement. Long-term datasets inform habitat placement and structural reinforcement strategies. Scientific exploration integrates seamlessly with operational logistics. And as infrastructure matures, lunar orbit transforms into a staging hub. Vehicles refuel, reconfigure payloads, and depart for deeper missions. The moon's reduced gravity well lowers energy requirements for onward travel, making it an ideal launch point for interplanetary expeditions. Transportation architecture expands outward organically, and public-private synergy continues to drive momentum. Government agencies define exploration goals. Commercial entities provide scalable transportation and manufacturing capability. Shared milestones align incentives while distributing risk. Transparency and progress builds trust across stakeholders, and continuous improvement culture sustains advancement. Every anomaly becomes an engineering dataset. Every successful mission validates design assumptions. Iteration cycles shorten further as experience accumulates. Scaling principles remain consistent. Build, test, analyze, refine, repeat at accelerating cadence. And through disciplined execution, integrated systems engineering, and unwavering focus on reusability and scalability, sustainable presence extends from concept to operational reality, reshaping humanity's relationship with space through infrastructure, designed not for a single achievement, but for enduring expansion. NV